Welcome to Quantization in 4 minutes. So, the story is how to take a classical system into what we call a quantum system, a story that is from physics, formally set into mathematical terms. Well, as known, a classical system is defined as a triple of a manifold, a symplectic form, and a vector field, being this symplectic manifold the cotangent bundle of a configuration space. And by the way, if this configuration space happens to be Rn, then the cotangent bundle is of course R to n. And by choosing canonical coordinates, you can naturally have an expression for the vector field induced by the Hamiltonian. So our primary goal here is to find a map that takes classical objects into their corresponding quantum objects. What we are trying to do is to find a quantization map, which is taking functions over the Poisson algebra of the manifold into operators over the Hilbert space. So we are taking the Poisson algebra over the algebra of operators in a Hilbert space. That's what we are trying to do. And such a particular mapping must indicate to us how to map, for example, compositions and the Poisson bracket, namely the so-called von-Neumann rule and the Dirac axiom, among others, but these two are particularly remarkable. Long story short, the quantization of Q and P are as shown, being Q the multiplication by it. And we can happily quantize any function from the algebra of the manifold as long as it depends on Q and P. You just have to quantize term by term the Taylor expansion. But, because there is a but in this story, as soon as you try to quantize functions including cross terms, for example PQ, we can easily find a contradiction because the von Neumann rule is very clear on how to quantize compositions, and you can find two different quantization for the cross term PQ. They are different, leading to a contradiction. And this is example, easy example, among others, a straightforward example of the incompatibility of the axioms of quantization. And taking the Dirac axiom, it makes us think in how, in the famous property of commutators over the Lie algebra, and we can propose a new formula for quantization as shown. The problem is that if you plug in one in, then you are not mapping the identity over the manifold onto the identity over the Hilbert space, which is of course a problem. It is possible to easily correct this by adding an extra term, which is just the multiplication by the function. But now, if you try to quantize the Poisson bracket, it breaks the rat condition. Remember that you have to map the Poisson bracket onto the commutators. And now, we trying to save this, we choose a symplectic potential, which is a tautological one form, with the property shown in the slide. And by doing the right computations, it leads us to a new formula of quantization, but now we have a unicity issue because you can locally choose different potentials and you can have a different quantization for the same function. But if we rewrite the symplectic potential in terms of transition functions, we can define a line bundle, and now the functions over the Hilbert space the operators act on can be defined as sections of this line bundle. And we can identify a connection, the definition of a connection in the new formula for quantization. And therefore, we end with this new formula for quantization. And roughly speaking, this is the story of geometric quantization.